All right. So 3.4. Yes, I think it is recording now. Yes. Okay. So 3.4 starts to take a look at what it means to have derivatives as rates of change. Okay. Now we talked about that in the front end, that we had sort of this average rate of change and this instantaneous rate of change. And one of those was secretly a way of saying derivative, right? Which one was it? Was it the average rate of change or the instantaneous rate of change? Yeah, exactly. That instantaneous rate of change is indeed a secret way of saying derivative. Okay. And in particular, we also looked at this formal definition of a derivative. And so that would be something that I really want to make clear, that when you see the phrase formal definition, you have to use the formula that we were given for that, meaning the limit as h approaches 0 of those 2 points that are super close together. Okay, so when you see formal definition, that needs to say in your brain, oh, I need to use that limit as h approaches 0 business. Okay. Now, we've also since then learned a bunch of shortcuts, right? Instead of going through this formal definition every single time, because my goodness, can you imagine if we had to do that for product rule and quotient rule? Like, that's just such a mess. So we have all of these special rules for the derivatives that we tend to see most often, okay? And so what we're going to talk about right now is, how do we apply the concept of rate of change to things that move? Okay, meaning how do we actually root ourselves in an understanding of what this might mean for any kind of motion? Okay. So let's take a look at this first example here. Okay. So the equation of a motion of a particle is S of t equals 2t cubed minus 5t squared plus 3t plus 4, where t is measured in seconds and s is measured in centimeters, okay? And so we have this graph here. And so if you put this on Desmos, you should get a picture that looks something like this, okay? And I'll leave you to confirm that on your own time. But I'm wondering if we can use the information on our graph and from the equation to answer parts B and C, okay? So part B says, find the initial position of the particle from the graph, right? So I'm wondering if from looking at the graph, you can tell me, where does that particle start initially? Yes, and initially meaning t equals 0. So what is the position at t equals 0? Lovely, lovely. Okay, so I'm going to zoom in on this graph. Initial means when we start counting time. And for us, that typically means at time equals 0. Okay. So the initial position of the particle graphically is 0, 4. All right. Another way of saying that is we looked for the y-intercept, right? But we could also say s of 0 equals 4. So all three of those would say initial position of the particle. Okay, and the key thing here is that initial time. Okay. Now, in true Judy fashion, I also want us to know, how can we find the initial position of the particle algebraically? So let's pretend for a moment we didn't have this lovely graph with points on it already. How would we find this initial position algebraically? All right, I love it, I love it. Initial position means t equals 0. And so we are going to do exactly that. We're going to grab that equation, and everywhere we see a t, we're going to put a 0. So 2 times 0 cubed minus 5 times 0 squared plus 3 times 0 plus 4. All right. Lots of things go to 0, and lo and behold, s of 0 equals 4. And that's great because it matches the point we chose on the graph. It matches what we said was the y coordinate or the y-intercept. That matches that initial position. Okay. Now this, I want to be really, really clear about this. This is a graph of position. So this tells us where a particle is at any given moment in time. Okay. This is actually very similar to the graph from 3.1 with the two runners. Okay, so I don't know if you remember that graph, but there were two runners. Runner A sort of went at this very constant speed, and runner B started off slow, but then picked it up at the end, and they managed to finish in a tie. All right, that was a position graph. All right, so it told us where they were at any moment in time. But from position, and you folks actually sort of started to catch on to this, from position, we can actually get velocity. Okay, so this is one of the cool applications of calculus, is we can use a position function and get the velocity function. And it turns out that when you're looking for the velocity function, velocity is nothing more than the first derivative of position. Okay, let me say that one more time. Velocity is nothing more than the first derivative of position. So we have our equation. We have our equation for our velocity, or sorry, for our position. 2t cubed minus 5t squared plus 3t plus 4. And when we use the power rule to find that derivative, we end up with the velocity function. In other words, the slope of this curve tells us about the velocity. Okay. So if we use our power rule, we'll end up with 6t squared minus 10t plus 3 as our velocity function. Okay. So really important concept here. Velocity is the first derivative of position. Okay. Now, if I showed you this graph, all right, the position graph, and I said, where is the slope equal to 0? What would you say? Maybe I can zoom in a little bit here. Where would you say the slope equals 0? Yeah, like somewhere in that middle part, right? Somewhere in here, we think that that slope is going to be 0, right? And what are we looking for? We don't want a tangent line like that. That would not be a slope of 0, but we're looking for something where that tangent line is horizontal, okay? But with this graph, you can tell it's kind of hard to get an exact value, right? The way that if we zoom in, we still might not be able to find the exact place, right? Like x equals 2 is over here. That looks like it's got some sort of positive slope to it. So I don't know, somewhere in here, but it's really hard to tell exactly. So that's where this idea of a derivative comes in, right? Because when a particle is at rest, is it moving? No, it's not moving, right? So when a particle is at rest, it is the particle is not moving. So v of t, what can we say about the velocity? It looks like, Matt, you already got that in there. The velocity is going to equal 0. Okay. Well, let's see. Where is the velocity equal to 0? I wonder if we look at the velocity graph, is it easier to tell where is that velocity 0? Oh, okay. So let's go back for a moment. We're looking for when the velocity equals 0, right? This is a graph of velocity. So we could say this is time. What would we label the y-axis as? Yeah, this is going to be velocity, right? So any y value tells us about velocity. So if I want the velocity to be 0, another way of saying this is y values on velocity graph equal 0. Does that make sense? That if we're saying, I want to find the velocity when it's equal to 0, all we're looking for is the y values on the graph being equal to 0. And so if we look at what we have, this coordinate, which is this one right here, has a y value of 0. And so does this one. So 0.392 and 1.274 would be the two moments in time when that particle is not moving. And so we can write that here to complete our answer. We can say t equals 0.392 and 1.274. Okay. Yes, and Luca, that is exactly what makes this tricky. All right, we're looking at a graph, and this graph, this blue one right here, the velocity graph, that is actually a graph of the slope of this graph. Okay, and that kind of messes with us a little bit. And so one suggestion I have is to make sure you know what the y-axis is telling you. So in velocity, this is velocity. But if I were to go back to the position function, I would say that this axis is position and this is time. Okay. All right. So we have a function. We can find position from it. We take the derivative, we end up with velocity. Why stop there? we're going to take the derivative one more time. All right. We take the derivative one more time, that second derivative, and we actually end up with acceleration. Okay. So a of t, acceleration, yeah, one more time, is the first derivative of velocity, but it is the second derivative of position. Okay, so first derivative of velocity, but second derivative of position. And so if we grab our function from above, let's see, what did we have for v? We had 6t squared minus 10t plus 3. So we'll get 12t minus 10. 12t minus 10. Okay. So we've determined the acceleration function by taking the slope of the velocity function. Okay. And this one, 12t minus 10, I think is not so bad for us to see on the graph that this has a y-intercept of negative 10 and then a slope of 12. Okay. All right, let's take a look at question C here. When does the particle have an acceleration of 0? Okay, so when does this particle have an acceleration of 0? What are our thoughts on that? When y equals 0, okay, because let's see, with this graph, this is a graph of acceleration. That means that this y-axis is acceleration. Okay. All right, so what we're looking for then is when does a of t equal 0? All right, so when does a of t equal 0 is another way of saying this. Check out what we have on this graph. We've got a point, 0.833 is the time when that particle is not accelerating. Okay. How could we confirm that algebraically though? How could we confirm our answer using equations rather than graphs?
Set that second derivative to 0, solve for t.
Exactly, exactly. So we're going to take 12t minus 10. We're going to set it equal to 0. We're going to do a little bit of algebraic manipulation. We get 12t equals 10, t equals 10 over 12. And let's go ahead and reduce that for good measure. We've got 5/6 for our moment in time when the particle is not accelerating. Okay. Let me show you something really cool about this. 0.833, right? Let's remember that number for a second, 0.833. That's when the velocity is, or when the acceleration is 0, right? This is when acceleration equals 0. How is acceleration related to velocity?
Will that be like the lowest point on that previous graph?
It might be. Tell me before we get there, though, how is acceleration related to velocity?
Drawn a blank.
Totally valid. And that doesn't have to be just you. Is there anyone who thinks they might know what the relationship is between velocity and acceleration? Ah, okay. Matt, be more specific. Acceleration is the slope of? there we go. Okay. So we said velocity, if I take that derivative, I end up with acceleration. Well, what does that mean? That means acceleration is the slope of velocity, right? Acceleration is the slope of velocity. And what this means is that if I go to 0.833 on the velocity graph, the slope there will be 0. Let's check it out. Draw this parabola. The very bottom of the parabola, where there might be what you were saying, Jeremy, a local minimum, right? Or the bottom, the slope there is 0. Okay, so if someone says, gives you a velocity graph and says, when is the acceleration 0? You would look for where the slope is 0. Okay. Now, we are being very particular in our language here. And Vince, I'm really glad that you brought up that word speed, okay? So speed and velocity are different. But when we think about like the order of the derivatives, it's position, velocity, and then acceleration, okay? Position, velocity, and acceleration. No. I wish they chose a different letter, right? S seems like it should be for speed because that's the first letter, right? V for velocity, A for acceleration. I don't know why, but position, we typically use S of T, or another common letter is we'll use X of T. Okay, so S of T and X of T both refer to position. Okay. Yeah. They could have named things so much better. But all right, so position is S as in Sam or X as in xylophone. I almost said X as in zebra, but that's not true. All right, so X as in xylophone, then we've got velocity, then we've got acceleration, okay? And all of them tell you about the slope of the one that came before it. So let's take a look at maybe a slightly different picture, okay? And walk through that same idea again. So in this case, we have the equation of motion of a particle. So position is t cubed minus 3t, where t is measured in seconds and s is measured in meters. And what we want to do is, if we put it on Desmos, we should get this graph, okay? And let's remind ourselves, how do we find that initial position from a position graph? Good, great, Sophia. So we're looking for when time equals 0. So graphically, this would be the y-intercept. And in this case, that is 0, 0. And we could also think about that as S of 0. So this point right here is gives our initial position. Okay. Now, how do we find this algebraically? Turns out this last piece tells us what to do. We're going to plug in 0 into the position function. So S of 0 equals 0 cubed minus 3 times 0. We want to be really careful about our computations. I've definitely seen people move through something like this too quickly and they get -3 just because they forget that 3 times 0 is going to give you 0. But you should end up with 0. And if we're going to start to bring in units here, what units might we want to put on our answer for C?
Meters.
Okay. So let's think about what we're asking for. We're looking for initial position. So we don't want to have seconds because that would be time, but rather we're looking for meters because that is where we start. Does that make sense? I know they're both 0, but we're looking for like the Y value. What units are those? And so it might even be helpful to write S and then put in meters and T and put in time on your axes. Okay. All right, we got one last part for this position question, which is find the average velocity over the interval 1 to 2. And draw the secant line on the graph to the left, okay? So if I were to draw a secant line, maybe we actually start with the secant line, what would the coordinates of those points be on this red curve? Oh, 1 point would be 1 comma -2. And this 1 is that 1. All right, I like that. I like that. What's the coordinate of the second point? 2, 2. Okay. So if I were to do this in a different color, I get this point, and that X value comes from the second number. Okay, so in brackets, those two numbers represent X values, and then we can go to our graph and find the Y values that go with them. And if we're looking for our secant line, we're gonna try our best to draw a line that goes through both points. All right, so that secant line there is this secant line. And what am I asking you to find in part D? I mean, I know it says average velocity, but what am I asking you to find? Excellent, excellent. We are looking for the average rate of change. Okay. So one thing that we might want to take away from this is the average velocity is the average rate of change on a position function. Okay. So when someone says average velocity, you want to look at the position function. Okay. And you're going to find the slope of that line. And so we'll get slope equals, let's see, 2 minus -2 over 2 minus 1. And that gives us a slope of 4. And what units would I use for the average velocity? Good, meters per second. So we're gonna go meters per second. And that is our average velocity, okay? Now, you can imagine finding the average velocity is not so bad on the position function, but finding the instantaneous velocity is actually a little bit trickier, because if we picked a point and we're trying to draw a slope, we're estimating really, it's harder to find the actual value. And so that might be a really good reason why we need a velocity function to look at. Okay, so let's take a look at this velocity one. This is the velocity function of the one we just looked at. And so it might behoove us to write v of t equals s prime of t, meaning we're finding that first derivative. It's like you read my mind, Matt. And if we go back to our function, which was t cubed minus 3t, we'll get 3t squared minus 3. Okay. So just using that power rule, finding that derivative. All right. And if we graph that, I hope we expect a parabola that is facing up And indeed, we have a parabola that is facing up. Okay. All right, talk to me about this question. When is the particle at rest? When is that particle at rest? And more importantly, how do we know? All right, so when the particle is at rest, that means that the velocity equals 0, right? Because nothing is moving. So there's no rate of change because it's just sitting there, okay? And so from our graph, which point would we want to choose from the graph? Nice, nice. Yeah, this is going to be the same as looking for an x-intercept on the velocity function, okay? And since we're saying we're starting at time equals 0, we're really just looking at the right-hand side of this graph, okay? But you are totally valid, Abby, that if I hadn't specified that, -1 would have been another moment when that velocity was 0, okay? All right, how do we find this from the equation though? We're gonna grab that velocity equation. We're gonna set it equal to 0. Right? When we're setting it equal to 0, that means we're finding that y-intercept or x-intercept. So we'll get t squared equals 1. Now this next part is actually really important. All right, when I take the square root of both sides, I'll better get 2 answers. Okay. I know I just said in response to the other one that of the 2 points, we only want one of them. But it's important to get in the habit of saying plus or minus and then saying only t equals 0. Okay, so taking that time to say, I know that a square root is plus or minus, but I also know when we're looking at velocity, we're starting from time equals 0, so I don't have to worry about the negative one. Okay. All right, thoughts on how we find the average acceleration from our velocity graph? There you go. There you go. Average acceleration. This will be the average rate of change on the velocity function. Okay, this will be the average rate of change on the velocity function. And if we were to draw our 2 points, we would choose that 0, -3. And the second point would be 1, 0. And we could draw in that secant line. And we could plug in some numbers to find the slope. All right. And so we'll get slope equals 0 minus -3 over 1 minus 0, which should give us a slope of 3. And what are your thoughts on the units for this? What do we get for the units? Nice, nice. Meters per second squared. And if you're not sure where that came from, folks, it might be useful to think this is time, right? So we're measuring this in seconds, the x-axis. And the y-axis, we're measuring velocity, and that's going to be meters per second. And so when we think about the units for the top, we get meters per second. On the bottom, we have seconds. And so overall, we have meters per second squared. Okay. All right, we're going to finish up this example here with the acceleration piece, and we'll call it a day. So, acceleration function. We can get our acceleration function by finding the first derivative of velocity. And since our function was 3t squared minus 3. When we take that derivative, we get 6t. Okay, so just using that power rule. And we've got a graph here, slope of 6, y-intercept of 0. And the last question we're going to answer today is this. Find the acceleration when the velocity equals 0. Okay, so talk to me about some problem-solving strategies. How might we approach this? Find the acceleration when the velocity is 0.
Um,
I like these ideas here. Let's write them down. So it says, let's see, we have one that says a of 0. So we plug 0 into this. Now, if we think about what we're doing here, we're plugging 0 into the acceleration. That means this will give us the acceleration at time equals 0. Is that the same as when the velocity equals 0? And I would say that it's not necessarily true. It might coincidentally be that, but acceleration at the initial time is not necessarily when the velocity is 0. Okay. And so great idea, but not quite appropriate for this particular question. All right. So let's see what we have here. We have velocity of 0. Okay, what does this tell us? V of 0. What does V of 0 tell us? Yeah, this tells us velocity at t equals 0. Is that the same as when the velocity is 0? Okay, so that's also really important. A lot of times I find that students panic plug numbers in. They're like, I don't know, it says acceleration, so I'm going to plug 0 in because that's the word I see and that's the number I see. Or maybe you're like, oh, I see the word velocity in 0, so I'm just going to plug 0 into velocity, right? But what I'm encouraging us to do here is really unpack what that sentence is saying. So when it says velocity is 0, that means velocity is, so is equals 0. Okay, this statement says velocity is 0. All right, so we do want to start with v of t equals 0. And so that does require us to go back up and say, oh, hey, what was my velocity equals 0? And check this out. We already found that, right? Velocity equals 0 when t equals 0. Okay, so from above, we know that happens when t equals 1. Okay. T equals 1, however, is not my answer because I don't want to know about time. I want to know about acceleration. Good. So this might be our first step. And the second step would be a of 1. So 6 times 1 gives you 6 meters per second squared. Okay. And so this, I think, is a really good exercise in terms of unpacking a question and making sure we know what the different pieces mean and how to take a question and write it as an equation. Okay, such an invaluable skill. All right, so we're going to stop here for today. I know it's been a long day. We have two more examples that we will finish up tomorrow. Okay, so we have two more examples that we'll finish up tomorrow, and then we are diving into the world of trigonometry. Okay, so be ready for that, to take a look at, maybe your unit circle would be a good thing to look over before you come to class tomorrow. And other than that, if you don't have any other questions, you are welcome to take off.